To take a complex mixture apart, brute force will fail. We have to identify and exploit physical differences at the microscopic level. We can diagnose these invisible differences using a beam of light. In a true solution, where particles are smaller than 1 nanometer, the laser passes straight through, completely unseen. But if the particles are between 1 and 1,000 nanometers, a colloid, they violently scatter the light, illuminating the beam's path. This is the Tyndall effect. This exact scattering happens at scale. When you see sports stadium floodlights carving bright cones through night air, you are looking at light bouncing off massive numbers of smoke and fog particles suspended in the atmosphere. Once we diagnose the specific size and physical nature of the components inside a mixture, we can build a precise trap to force them apart. If we have liquids that refuse to mix, we can exploit their densities. In a separating funnel, gravity does the work. The heavier blue liquid is pulled firmly to the bottom, allowing us to drain it away while trapping the lighter yellow liquid above. But if these two liquids share the exact same density, gravity acts on them equally. The funnel becomes useless. The droplets remain suspended, locked together in an emulsion that refuses to separate into clear layers. When gravity isn't strong enough, we manufacture our own. By spinning the mixture in a centrifuge at high speeds, we create a powerful outward force. In a blood sample, this drives the dense red blood cells straight to the bottom, pushing the lighter yellow plasma to the top. We can manipulate density to separate a mixture, provided there is a measurable difference we can capture or mechanically amplify. When two miscible liquids are perfectly mixed together, we exploit their boiling points. We apply heat until the liquid with the lower boiling point vaporizes. Those vapors travel up, cool down inside a condenser tube, and drip out as a completely separated, pure liquid. This setup requires a temperature gap of at least 25 degrees Celsius between the boiling points. If that gap shrinks below 25 degrees, both liquids risk boiling at once. We then insert a fractional column packed with glass beads. This creates multiple cooling surfaces, forcing the mixed vapors to condense and reboil until only the correct liquid reaches the top. Heat also offers a shortcut for specific solids. If we have a mixture of sand and camphor, we heat them together. The camphor bypasses the liquid phase entirely, turning directly into a purple vapor, while the sand is left completely untouched. By targeting exactly when a molecule changes its state of matter, heat acts as a precise tool to pull components apart. We can also separate components based on how fast they move across a medium. In paper chromatography, a clear solvent wicks up a filter paper, dragging dissolved pigments along with it. Because different colors interact with the paper at different speeds, a single black ink dot fractures into distinct ascending bands of cyan, magenta, and yellow. This graph shows a solubility curve, mapping temperature against how much salt a volume of water can hold. If we have a saturated solution at a high temperature, the water is at maximum capacity. As the temperature drops, the curve plunges steeply, crossing a critical threshold where the water simply cannot hold that dissolved solid anymore. Because the excess solid can no longer remain dissolved, it falls out of the solution. The cooling liquid forces the particles to organize, settling at the bottom of the beaker in precise geometric crystalline patterns. The result of this sudden thermal drop is a highly purified solid, cleanly separated from its surrounding solvent. Solubility is a delicate threshold. By manipulating the temperature, we force that threshold to break, leaving behind pure, isolated matter. Let's apply these principles to a final test. A single beaker containing a chaotic 4-part mixture of sand, dissolved salt, water, and oil. Step 1. We exploit density. Pouring the mixture into a separating funnel isolates the floating yellow oil. We trap that oil layer and drain the muddy, salty water out the bottom. Step 2. We exploit particle size. By passing that drained liquid through filter paper, the large solid sand particles become trapped, while the clear saltwater solution flows right through. Step 3. We exploit boiling points. We heat the clear saltwater in a distillation flask. The pure water vaporizes and collects in a separate flask, leaving behind a solid crust of pure white salt. Separating a mixture requires observing its properties and systematically exploiting them. Whether you target particle size, density, boiling points, or solubility, You now have the exact physical checklist needed to break matter apart.